I am here at GalaxEye in Bengaluru for an office tour and to meet 4 of the founders of the company to talk about mission Drishti. This is the first ever Indian satellite in space that is an OptoSAR satellite, which means that it does multispectral imaging as well as SAR imaging on a single satellite. This is the first time that this has ever happened in the world. I'm so excited to actually go in here, do an office tour, and find out more about this company. So come on, let's go inside. When did you guys settle on this problem specifically, putting SAR and MSI on a single satellite?
We started working on this problem statement right after COVID or around that time. Like Suyash, who was the CEO, he was working with TCS at that time, and they had a client who was a county in California, and they had issues in wildfire, and Suyash was given the task to help the county mitigate wildfire. So he used optical satellites, and there was smoke there everywhere. He couldn't understand anything. He knew that there is something called SAR that exists, synthetic aperture radar, or someone had mentioned it. So he tried using that data. He didn't understand anything. In Bangalore, in a cafe here, he was discussing the same thing with Rakshit. That discussion sort of started, hey, there is this issue, I'm not able to solve it. And from there, we started coming in together trying to help Suyash out on how to solve this.
As early as recent as 2020, there was no synced SAR and MSI imagery available to someone who wanted to purchase it?
There was no imagery. So we thought there would be something that would exist genuinely.
Because SAR has been around for a long time.
SAR has been around for a long time. Optical has been around for a long time, and we thought that this would exist. There have been research papers, lots of them, that talk about the benefit of fusion, and but same thing, we tried doing fusion on existing satellite data, but again, the satellites that existed back then, they were not doing fusion from the same satellite. So like there was no data product called OptoSAR, like optical and SAR together, so you would get optical data from one satellite at a particular time and SAR data from another satellite at a particular time. There were many problems that happened. That optical would be at nadir, it would be usually in the daytime region, SAR would be at night. For a layman, what the person will try to do is look at the SAR image and an optical image and try to understand, hey, what is actually happening in the SAR image. Eventually we thought, if we want to solve this problem, we need to build our own data set. And that's where we started thinking, let's build a satellite that will have both SAR and optical satellites together, and the data set that we get from this satellite will help us make satellite imagery more reliable. March 2020 we started dabbling into the problem statement that we had, and I think May 2021 is when we officially incorporated the company. Let's start building the satellite.
Were there any people at that early stage who said, don't do this? This is a bad idea?
Many people said that. So we talked to a lot of ISRO scientists. Many people all of them were shocked that this data should have been existed. Why are you launching a satellite? Many people were just in denial that there is no data set like this existing. You should not launch a satellite because you'll get the data. Someone would have done it.
The data is there, you just need to figure out how to sync it.
Yeah, or there are satellites that might be doing it, you just don't know. We had done a thorough study. Till now also, there are no satellites that give you OptoSAR data fused together. Many people said that, okay, it's a very difficult technology, synthetic aperture radar, you won't be able to build it. And many people came and said, don't try this.
Tell me about that, building SAR itself. What actually needs to happen in order for someone to build their own SAR system?
We have some prototypes here.
Yeah, why don't we actually, so these were the early ones. This was the earliest one, right?
This is the earliest antenna that we had.
Okay.
We bought this from our first grant money. We got around 4-5 lakh rupees.
Oh, you bought this? Okay.
Yeah, we bought this, yeah. So we were trying to understand SAR ourselves, how radars actually work. So synthetic aperture radar is a very specific type of a radar you use in a particular manner, you operate in that particular manner, and then you get a signal which can generate image. So now you have to do a very complicated signal processing on top of it, and you have to get actual signal out of the noise and create an image. This entire process for us took around 2 to 3 years. So we got our first SAR image on 4th May 2023. So not 2 years after incorporation. So we built
3 years after starting to think about.
Yeah. So and many times in the middle we thought, okay, this is very difficult. We are not getting an image. All we are getting are some. Even if we put a very high signal source, we are getting like a blip of the signal. So it took a lot of time for us to understand where the issues were going on. Sometimes the radar would not perform correctly. Sometimes the configuration would go bad. Sometimes our signal processing would go bad. All of this has to be correct. Then you have a SAR.
So what is this?
This is a horn antenna. This is in the X band region. X band is something that goes from 8 to 12 gigahertz. You send an analog signal, like a voltage signal here, and that it will convert that from to a free space radar signal. So this is one sort of an antenna.
How much did this cost to make?
I think this was around 40,000 rupees. This was around 1 lakh. So we needed 2 of these at that time.
It looks similar though. How is it more than double the cost?
So this actually has a much better performance than that one.
Okay.
Just because of the way it is designed, it allows the signal to come out more smoothly. But then afterwards we started designing our own antennas.
Okay.
So this was one of the first antennas that we designed. There were 2 of these that we would put. You can see that it is not that good workmanship, but yeah, we built it in-house in our lab. Then similarly, slowly and gradually we started going to better and better antennas. So we started figuring out what helps, how to change the antenna design also. So not only, so everything had to be modified again and again to figure out what might work for synthetic aperture radar. Another aspect is this could only give a resolution of somewhere around 50 to 60 centimeters. The more and more better we got in antennas, this can now give a resolution of as good as 10 to 15 centimeters. So that's how we figure out other aspects that can help the signal better. So this is another prototype we have built. So usually a radar is divided into 2 parts, a transmitter and a receiver. So the transmitter is what generates the actual signal, amplifies it accordingly what you need, and then the receiver is what takes the signal that is reflected back and then does noise correction and all the, like you want to remove the noise and amplify the signal. So it does all those characteristics and then sends it to a digital acquisition system. So that takes the analog signal, converts it to digital, and then now we can store it. So
this one was actually mounted to a drone, right?
That is correct, yeah. So we...
Is this the one that you got your first image from?
I think, so what we got our first image from looked very similar to this. It was slightly bigger than this. But every month we had a new prototype. So what we actually got our first image from, we only have a dummy model of that. The actual one was the same. We opened everything, we modified a lot of things. So it's like, it might be like version 15 or version 20 of the first gen.
Sure.
Similarly, we modified other aspects as well. So we brought down as we understood how to build a SAR, we started optimizing on everything. And currently we have a SAR that can go, that is less than 2 kgs. So which can fly on a drone like that. Yeah, which can fly on a drone like that and take images from distances as far as 10 kilometers. So this learning gave us an understanding of how to also make a very optimized SAR. GalaxEye is only the second company in the world to have built a SAR that can fly on a drone. There is only one American company that has done till now. and it is all restricted in ITAR, so it never comes out of USA. These concepts of synthetic aperture radar we need to fuse with the concept of space engineering. So we need to figure out how to scale it up, and need to figure out how to make it so rugged that it can survive launch and it can survive space. Those are aspects which we learned separately by doing other missions, like we did a POEM mission, which is we mounted a part of this payload on of the SAR. We took a small part of it, made a small payload out of it, and launched it on PSLV, ISRO's rocket.
PSLV 60? C60?
Yes, PSLV C60. This was launched on 30 December 2024. So that helped us understand how to build a space grade system. And with that, so all these learnings we slowly got together, and now we know how to build an entire SAR for space, not only SAR, satellite for space.
Another thing, right actually behind us, is this system over here, and I'd love to know the story behind this, because we have it right here. So this, I believe, was this meant to be mounted somewhere?
Yeah, so this was actually mounted on the nose of an aircraft. So before building a SAR for drones, we thought for us to understand how to build SAR, an aircraft would be a better test scenario, because it is much more similar to a satellite, and drones are very unstable. So it makes the signal processing part very, very difficult. Everything is moving around. So aircraft was the obvious choice to do our first testing. So we took help of some of our advisors, and we understood that there is an aircraft that exists with DRDO, which is the only aircraft in which we can put our X-band radar, which has a radome in front of it, which is made up of Kevlar, which is transparent for radar. So all those things, we somehow found an aircraft where we can do this testing. Other option was that we can go take this payload outside India and do the testing, let's say in Europe or Australia, where the regulations are more freer. You can take a radar and you can fly. But taking a radar out of India has its own challenges. But yeah, so this is our first synthetic aperture radar that we built. It gets mounted to the aircraft on this side, and imagine there's a nose cone coming like this. It sits inside that, and via this antenna it transmits everything. This is a system that sits inside the cabin, which stores all the data and controls the SAR from inside. This is what we had designed to get our first image, but we could never fly this. We couldn't fly this because of certain policy related requirements, where there was no policy where an Indian company can fly a radar for themselves, because no one had tried this before in the past. Only way to test a radar on an aircraft was, let's say you have won a particular defense grant, and for the purpose of that, the defense agency would give you permission to fly it for yourself.
For them,
for
basically.
them.
Okay, got it.
But we wanted to do R&D. We didn't have any particular customer.
Was there a thought that maybe you'd take this outside of the country and fly it there?
There was a lot of thoughts there. That required other challenges, that we need to get something like a SCROMET license. This is a license you need to get for exporting restricted items. This is a synthetic aperture radar, so it comes under it can be used as a dual use system. Most of the fighter aircrafts, they have a synthetic aperture radar in them, and this was also tested in the nose of an aircraft. So there were many challenges.
The red tape makes sense.
Yeah.
It's there for a reason.
Correct.
But also it caused a lot of issues for you and your company. So you spent, are you able to tell me how much you spent on developing and mounting this system before you found out that it wasn't possible to fly it?
So we spent more than a year and almost most of our pre-seed money.
Okay.
We were able to save significant amount of money, and we were able to salvage a lot of the components. And as soon as we figured this out is when we quickly shifted to let's build SAR on drone. We did more than 500 flights on drone and more than 10 different prototypes on drone. So in hindsight, whatever happened was good because we had a bias that we can't do SAR on drone. Like people would tell that you can't do SAR, we ourselves thought we can't do it. But then when the situation came,
you were forced to.
We were forced to, that we have to do this or the company would not survive. So we did it. We became only the second. At that time, we didn't know that, at that time, publicly, no one had ever done SAR on drone. So 4th May, the first image we got was, you can assume that was like a lab prototype. If the situation is ideal, you would get an image. Soon we improved that even better, that no matter what happens on the drone, how dynamic it is, you will get an image. And you will get a crisp, sharp image as good as or better than what you would get from a satellite. Again, this facility is being upgraded right now. So
sure, this is brand new. You guys moved in, what, 4 or 5 months ago?
More than that, around 6 to 8 months ago, but we're getting the funding to scale it up. So earlier in our previous facility, the lab was very small. I mean, it was as big as this room at that point.
Oh, wow.
That was the entire lab.
That was the entire lab.
And that was inside the city in Bangalore, so we couldn't do much. We had to get a lot of permissions to even build it.
HSR layout.
HSR layout, yeah.
Okay.
So here
what happens in here? Because this is actually, I think this is quite an interesting room.
So here we do a lot of our modifications on our hardware. So what you see exactly here is, let's say, anytime we design a system or a radar system or a digital system or a PCB, you can't go and make new models and manufacture them again and again. So if you want to do some basic modifications on the system, we do that directly on the PCB here itself. And we test out, go to the field, test out is this modification helping or not. All these things start from the drawing board where the team upstairs say, hey, I think the design can be slightly better if we do this minor modification. So whatever PCBs we design, we keep it such that later on we can do some modifications here in the lab itself. That's how we have launched many prototypes. Similarly for satellite as well, this is the approach that we take usually. Before you come to the final design, you make multiple models and then you figure out what is the final model that will go into space. For this also we have something in space, we have different milestones that we call. So you have something called when you start any project, you have something called a mission concept review. So that's where you are identifying what are you going to build, how are you going to build it, you freeze all your requirements or the preliminary requirements. Then you have a preliminary design review. A preliminary design review is where you have built your first hardware and then you've gone and done testing of it, what we call hardware in loop testing. So you take that hardware, connect it to systems like this. So this is basically a spectrum analyzer. A spectrum analyzer understands how good your radar signal is. Similarly, there are oscilloscope, logic analyzers, multiple systems. Sometimes we create our own test systems. We test that out and then you go into something called a detailed design review or a critical design review. That is the stage when you have done all your modifications and you have frozen the design and it can go into mass manufacturing. Now I can manufacture another one, which is what we call the flight model. So that comes and all that has to happen before the next milestone, what we call the material readiness review. So in material readiness review, we have all the satellite components assembled and ready on a table so that we can start the assembly of the satellite. Then the satellite goes through its assembly and then there's a separate qualification of the satellite, full built satellite. Once that passes, then you have to submit that to your launch vehicle provider, let's say it's ISRO or SpaceX or whoever, and they review it and then they give a go ahead, you are safe to launch. or you will not damage any other satellites on the rocket.
So I think you guys had to go through multiple rounds of this, right, before it was ready for SpaceX?
Yeah, so we had to go through multiple rounds of the different subsystems. We had to go through multiple prototypes of that. They failed when we did testing. We also built something called a satellite structural qualification model, so or a satellite SQM. So that's where we test out the satellite structure. That also went through multiple failures before we identified what the issue was and we solved for it. And when we build, you do all these separate models so that when you assemble the flight model, you don't have second chances, because if you have to disassemble the satellite, that is a big risk. You might have to many times replace the structural parts. So we went through multiple cycles of the different qualification models, but when we built the satellite, that passed on the first go.
Okay, that's great.
Yeah.
That must have been a huge relief.
Yeah, so that happened. So that's what our deadline to give to SpaceX was 20 January. We gave to them the results on 20 January.
I thought you were going to say 19th January.
Literally on the last date, we had sent the data. We knew the critical part we had passed around 17th January, but again, we were against the time. So there was no room for any failure, any error on the flight model. If that would have failed at that time, we would have to rebook the entire rocket because that was too late.
Yeah.
They would not push our rocket. They would be like, they would have launched without us, and we would have to book another slot on the rocket completely.
Do you lose your deposit in that case?
If you fail at that late in scenario, you do lose all the money that you sent.
The whole money?
Yeah.
Even if you're not there in your slot, you lose it all.
You lose it all because it's very late in the program.
Yeah.
So usually you can change things and you can still until like 3 months before launch. SpaceX would have helped us out. They would have agreed that we are a startup. So I don't want to go into scaring anyone for this, but usually you can't change anything. You can't change anything like 3 to 4 months before the launch. You have to be very sure that I've passed everything. So this is the POEM payload, or the mission patch was. It's not a satellite, it's just a payload. So this is what we launched to space for the first time. So inside this there is the data acquisition system of a SAR, and it is also an edge computer inside. So what we did here, we packaged some of the components from the drone-borne system. We identify what would not work in space. In the lab that you saw, we manually removed the ICs, replaced them with military grade ICs or whatever was required. And whatever was available for, let's say, 30,000 or 10,000 in the market, we made it space grade. And
this doesn't have any propulsion. It's just a box, basically.
It's just a box. So what would happen is that this would sit on the 4th stage or the final stage of a PSLV rocket, and the PSLV rocket would provide power to it. It will ensure that it is in space for around 3 months, and we have to go to ISRO or like ISTRAC, where they give us access to our payload, and we send commands to the payload and operate, and we do our operations. So what we did here was from the data that we had from our drone-borne SAR payload, we created an image in space. It was a complicated procedure, but it tested a lot of our radar components and a data acquisition system. We also processed the entire image from raw to an usable image in space, and then downlinked that on ground. All that happened, and we tested this system in various scenarios. We tested it in less than minus 10 degrees Celsius. We tested this in what we call South Atlantic anomaly. That's where there's a lot of radiation present. In all of that, it survived. So it will be the biggest satellite launched by a private company in India. So this weighs around 185 kilos, and again, when fully deployed in space, this entire wings, they go for somewhere around 3.8 meters. Once the satellite is separated from the rocket, it automatically turns on, and it has the software takes over and starts stabilizing the satellite and deploying the antenna. So all that happens within the first few hours post launch. There are solar panels behind the antenna of the synthetic aperture radar. So at the bottom, what you see silver is the radiating part of the SAR antenna. Behind is the solar panel. So this is a unique aspect that we brought in to save a lot of the mass, to make it more compact. Many satellites, they don't do something like this. This makes things a bit more challenging in terms of thermals. But we found a way to solve it.
So do the SAR panels tilt, or does the satellite itself tilt to achieve the angle that needs to be achieved for the SAR imaging?
So the satellite completely tilts to whichever location required.
And the MSI unit, does that tilt?
Yeah, so nothing. So both, so that cylinder that you see in the center is this multispectral imager. It's a dummy here. And they both are aligned in such a way that they will look at the same location at the same time. We have aligned it to an accuracy of 0.03 degrees. That is required to do what we have done.
So I'm sort of surprised, and maybe it's just because I don't know enough about the industry and how difficult this is, but it is surprising to me that no one else has done this before. Why is that?
There are a few angles to it, and I would say people have tried to do similar activities, but not this particular activity. For example, few people have tried getting the two images from two different data sets which were required, in very less time difference, and then they started fusing it, but then they got some false positives, they got some discrepancies, and the whole mindset went into how to solve those discrepancies.
Would you say that that's the industry standard right now? Have two separate satellites, one for MSI, one for SAR, and you sync the images together?
Correct. And they tried to fuse these two images at the image level, right? And all the research and work is now, and they started doing it to how to fuse it at the image level. What we tried to do is solve at the source level itself, right? So that's a different part that we took. But many people in the industry already started working on fusing these two data sets. There was also one more program by a company in Canada, I am forgetting its name, but they wanted to have two satellites, one optical satellite and a SAR satellite, one behind the other with some small gap, and then they again take images of the surfaces around similar time frame, right? And that was also one of the concepts that we studied when we started thinking about this problem statement. We found out that even if we take images 30 minutes to 1 hour apart, there can be some changes for some use cases, right, that we don't want. And that's why we wanted to have two sensors on the same platform. So I would say people had started thinking about this problem when we were also thinking. There were different ways people thought of solving it, and ours is a very unique way of how we are approaching it. And the second thought process is that there are again myths and biases that optical will look nadir, SAR will look always off nadir. So people who are always working on images and who do not have understanding at the hardware level will feel that it is impossible to do it as well. But if somebody who has worked on hardware and if he gets a requirement of this, he can work out a problem, a solution. Okay, if I do this, I can actually go and see both the sensors on the same platform and still get the images. So we got that benefit as well. Since we came from Hyperloop, we had developed hardware as well. And a few people, like Rakshit, have already worked on data. So we had an experience of data plus hardware, and that's how we were able to solve this from the source level and in a very unique way.
We have developed internally a foundation model called as S2O, which is SAR to optical. What S2O does is, once Drishti is live, it ingests all the data that Drishti collects during daytime in a cloud-free weather, right? So when there are no clouds during the daytime, it collects a lot of optical and SAR pairs which are synced with respect to each other in space and time, right? So S2O ingests all this data, and basically what it can do is, during the night time when it gets a SAR image, it can essentially regenerate an optical image. Or during the cloud time when there is no optical image, it can just ingest the SAR image and regenerate the optical image. So what this AI model is doing, it is learning from cloud-free OptoSAR images and continuously training on them, and then whenever there is an optical image not available and hindered by the clouds, it essentially takes a SAR image and converts it into an optical image, right? So what are the implications of this model now, right? First of all, you always have an optical image available for consumption, irrespective of what the weather and the lighting conditions are, right? Second thing is that if someone, an enterprise, has already built their AI models which run on optical data, which perform well on optical data, right now the models don't produce an output when they don't get an optical data. Right? With our S2O model and OptoSAR data sets, we provide an optical image irrespective of all these things, right? We provide a persistent stream of optical images, right? So they don't have to change their AI models. They don't have to build another stream of AI models that work on SAR. They can keep their entire processing pipeline constant and just add the variable of OptoSAR data sets, right? So essentially, their SLAs to their customers become more consistent.
I was just wondering, what is the best sort of current data set of the Earth? Like oftentimes for the average consumer, they think of Google Earth, right? I'm not sure to what resolution those images are, but they're pretty good.
Yes.
Right? So you can see like even vehicles sometimes close up. But that's, well, first of all, it's probably very expensive to capture that level of detail. And second of all, that's not updated very frequently. Whereas what you guys are building, the constellation that you're working on, will be, I think the conversation that I had earlier was once every 3 hours is the goal.
Yes,
right?
that's the goal.
Refresh. I call it refresh rate, but it's
revisit rate.
Revisiting,
yes. Yeah, so I think Google Earth is a platform that many people are familiar with, but Google itself does not acquire images. Rather, it has partnered with other companies that acquire that images at that resolution. And second thing is, Google does not update their catalog because primarily it's because it's more consumer facing and it's not the requirement.
Consumers don't need to see how things are changing.
Yeah. Second thing is, it's extremely expensive to acquire optical image at that resolution. Is extremely expensive, and it's not something that they would want to spend on to update it on a daily basis, right? So the implication of that is a lot of small changes. The world is much more dynamic than represented by Google Earth, right? So to capture those dynamic changes, if something has changed within 3 hours, to capture that kind of a change, you need a constellation that has the revisit of 3 hours, right? If something has changed in 24 hours, you need to have a revisit of 24 hours, right? Which is not the capability which is present in Google Earth. And that's why you need satellites. That's why you need a constellation of satellites which can deliver that much revisit. And apart from revisit, you need consistency also, right? So let's say you have optical satellites, SAR satellites, they are all taking images, right? But optical satellites don't offer you the consistency. They can offer you the revisit, but they will not offer you the consistency.
And that is because there's clouds and nighttime, daytime.
Absolutely. Just take an example of Bangalore, right? How frequently do you actually get clear skies? It's overcast. And in some regions, especially for tropical countries, see, this is one of the tropical countries, right, between Tropic of Cancer and Tropic of Capricorn. In this belt, the cloud cover is more, right, and hence the chances of having a clean acquisition is
No, there's sometimes where that you might have multiple days.
Yeah.
Where the clouds are there.
Absolutely.
What you're building, I think this affords a very interesting opportunity that we've probably never had before, but we're seeing it in other ways in other areas. So like, for example, OpenAI built ChatGPT, basically gave you all of the information that has ever existed ever in an interface that you can chat with. Unlike what Google used to be, where you could only get stuff that had been sort of indexed by their search engine.
Yeah.
We're hearing this term world model. It's actually it's been used in a couple of different ways.
Yes.
There's world models that are sort of like video game type models. There's also world models that help robots to interact with the world without like breaking themselves or breaking things. But I think now there's a new type of world model that perhaps, I'm not sure if GalaxEye is the first company in the world to be working on a world model like this, but tell me more about it.
We are planning to build the best embedding model for the world, which in our context is the world model. Best embedding model for the world, which will be the most detailed representation of our planet, combining and fusing information from different parts of the spectrum. And building this is like, building our own form of an internet, of the world's internet, and then, using it to build something like a ChatGPT of our own.
Yeah, an LWM. Maybe large world model.
That's a great name, by the way.
Yeah, or maybe an MWM because it's a massive world model. What are you going to call that? What is it going to be?
Not thought of it yet. The embedding we are calling Tessa, because we started from an apartment called as Tessa Maria, and we just thought that it would be a good idea to go back to our foundations and just give this ambition that name.
How would one go about interfacing with Tessa or whatever the large world model ends up being called?
If you are in California, right, and there were wildfires, pretty massive wildfires in California a couple of years ago, you can just ask that how are the wildfires progressing and what are the areas where I should be cautioned about going, right? And it will give you, on the map of California, it will tell you the progression over time of those wildfires, and it will also tell you, the red zones where you should be cautioned, right? Something very, very simple.
An LP. You're just typing in a prompt.
Yeah.
And you're getting an answer.
Yes.
Wow. So like, how bad is the traffic right now on Banarghatta Road?
Absolutely.
And how has that changed since the morning time?
Yeah, or sometimes when the ORR floods, you can ask, what is the level of flooding that has happened in ORR?
Which you cannot do right now with Google Maps.
You can't.
If you want to find out if a road is flooded,
yes.
I mean, I used to live on Sarjapur Road,
and
I would just have to find out.
Exactly.
Or I would have to watch the news.
Exactly.
Who does that anymore, right?
Exactly.
So wow, that's incredible. And again, it's going to be initially you're thinking every 3 hours.
Yes.
But potentially as the constellation grows, you might get even more
Absolutely.
Regular data.
Yeah.
So I asked the public on X if they had any questions that they wanted answered. Okay. And a couple of people chimed in. This question is coming from NSIND. They're asking, what are the launch timelines? And I have to imagine they're not just talking about, Drishti number 1, but the rest of the constellation.
By 2030, we want to have the first phase of our constellation. It will go to double digits. It's something which we are aiming for. Because we want to go and have a very low revisit time at a particular area on the globe. And we are targeting best revisits of less than 3 hours. So all of our constellation design and the number of satellites will be according to that. And we want to have this constellation by 2030, 2031 timeframe.
Having that 3-hour revisit time, what is that? I know what that affords in defense, right? Because you can track stuff in real time or semi-real time. But for commercial, that's what I was trying to figure out. For commercial applications, what do you think 3 hours would do? How do you think businesses would use that?
So, okay, we can take an example of one of the use case, which is disaster management and insurance. Okay. Now, at any given point of time, there would be some, natural disaster occurrence in the whole world, right? Now, point is when you experience a disaster and there is a damage associated to it, there is also a point of insurance coming in, and claims that has to be settled, right? Now, one point in that journey is that if the company can settle the claims very quickly, their rating goes high and they do better business. Now, to settle claims which are true and not false in very quickly, for that they would need information and the changes that is happening on the ground at a particular instant of time, right? And they would need at a better frequency as well. So that is one of the use case from a very commercial point of view that we can think of, in which you need a good amount of revisit time as well.
Yeah, and even outside of the context of natural disasters, if we're talking about insurance for the agriculture sector, for example, right?
Yeah.
Crop fire.
Yeah.
Right? Well, actually, the fire happened 2 weeks ago. It wasn't,
Yes.
as recent as you're saying it was, and we know because we are using GalaxEye.
Correct.
Yeah.
So for crops as well, but with the crops there is actually one more difficulty that nobody talks about. So we all know that for crops we need multispectral imager and those things, right? But in countries like India, when you want to when there is a rainy season or something like that, you would actually start harvesting crops around that time. And if there is that kind of a season, there are going to be clouds. So when you need a satellite image the most, you won't be able to get it. Or in one of the cycles of the whole production, if you need images at one phase where you are going to harvest, you don't get the images as well. And radar is non-intuitive, right? So that's where our vision came that we want to have a OptoSAR image, which is basically generated by having two, one SAR and one optical taken at the same time, and then we can use it. So as to remove the availability issue, as well as also make this whole Earth observation ecosystem a bit more reliable. Because when you don't have data or the data is coming at an ad hoc basis and it's not much reliable, you tend to try to find alternate ways, and that is one of the challenges that we believe OptoSAR will also solve.
Are you having to constantly sort of re-stabilize because you're at 500 kilometers, right?
Yeah.
Low Earth orbit.
So how we'll operate is that once we get a location of the area that we need to image, we will first get a confirmation of what is the look angles and how much the satellite needs to be oriented. Once we know for sure that these kind of look angles are required and a OptoSAR image can be generated through it, then we go and orient the satellite. Now comes how do we do the imaging. Now there are multiple ways in which a SAR can generate images, and with optical it's fairly single mode of taking images as of now.
The aperture.
Just take snapshots of the area, and you, as you keep going forward, multiple snapshots getting related to multiple bands will give you that whole MSI image. But with SAR there are two primary modes. One is you scan the area as you go along, and second is in second mode you stare at the area as you move along. So we can do imaging in both the ways and get the
staring, meaning that as the satellite moves, you keep the
looking
SAR looking at the exact same spot.
Yes.
Why would you want to do that versus scanning?
So what happens is when you scan a particular area, the resolution that you get in SAR image is a bit coarser. But when you stare at a particular target, the resolution becomes finer. We call it spotlight imaging in SAR. So yeah, we can have these two modes in SAR, and in optical we have one single mode, and then we fuse them together and get the OptoSAR.
I'd love to know, whatever you can share. I know you can't disclose a lot of information, but what kind of inbound interest have you received now that the world knows that you guys are building the first ever SAR MSI satellite?
For what we have done, and that is what we have done from the starting as well, is we have always kept customers in loop. So when we started, there was a program in IIT Madras called GDC, which forced us, and at that point of time, we didn't have our seed money as well. And at that early stage, they forced us to, talk to customers so that you know how much it is relevant. From that point onwards, till now, we have always kept customers in the loop, and we have always given them what is our progress. And the feedback that we have gotten is that they are very excited to see this kind of data sets. We have done some pilot projects with some Indian institutes, academic institutes. We have given the data sets. Of course, these were taken from our drone-based payloads, but these were also sync fused, and they used it for some agriculture purposes. And they were quite excited to see this kind of new data set. And they have already started doing their research on top of it. So the feedback is very, very positive. Everyone is looking for it, because what they get right now is 2 individual data sets from 2 different satellites. Even if they try to fuse it, there are too many false positives or discrepancies, right? So everyone is trying to, everyone is excited to have a first look of how this data set would look like.
Is it likely that majority of the companies building satellites and launch vehicles will go public versus being acquired?
Most of the launch vehicle companies, in my opinion, will go IPO. Right? Satellite companies, unless they're very clear about what they're trying to achieve, unless they're just, fascinated and they feel it's cool to build in Spacetech and they're building it, right? And I'm not sure about that particular, persona of the founder. But the founders who are truly, building for the future and they know what they're solving for, we believe that we know what we're solving for. I think they will probably go towards IPO, right? But the others may get into an acquisition mode here and there.
I've been saying this for many years. I just want to see more Indian brands and more Indian companies on the global stage, right? When I leave India, I want to go abroad and I want to see Indian brands, right? In the same way that an American kid growing up in the States travels outside and they see Nike, they see McDonald's. Spacetech is obviously a little bit different because you can't really see it with your own eyes, right? It's up there in space, your satellites. But I think that's one of the reasons why I like what you're doing so much, is that you're building this from India and you're building it for the world, but it's not just any service, it's not just any satellite, it's also a world first. I don't know, I guess there's not really a question there, but it must feel very, I'm sure you and the rest of the team feel very proud of what everyone here has accomplished.
When we came up with the concept of OptoSAR, where we're combining 2 things together on the same satellite, there were a lot of questions, why you want to build it, why don't you put these on 2 different satellites and then you get here and there. But we came backwards from the problem statement, right? And the problem statement is very simple. 70% of the Earth's landmass is always covered by clouds. I'm not saying, NASA is saying, okay? The solution was this particular technology called OptoSAR. We truly believe, this is global first. The kind of conversations that we're having today and the inbound that we get from outside investors, customers here and there, it is truly appreciating. It feels awesome. People often talk about, do we have a SpaceX of India? Do we have AA of India and all? I would like to say, do we have a GalaxEye of the US?
I love that.
Right. Do we have the GalaxEye of the Europe, right? And it'll become true. Maybe today, a lot of people will find this funny, but okay, 10 years later, 15 years later, we'll be able to realize that. In 5 years, we've moved very fast. From nothing to India's largest privately built satellite, world's first, OptoSAR. I'm pretty sure 20 to 40, 60 satellite constellation. And we want to kind of, bridge the gap of the right data that is not available in the entire world with this global first technology. And we're very driven to do that from India.